In our last video, we used the QR decomposition to solve linear systems of the form AX equals B, where A is a square matrix that we know, B is a vector that we know, and we want to solve for the vector X without necessarily having to invert A. Now we're going to focus on a special case where A is symmetric. And moreover, we're going to say that A is positive definite. So that means that if you take any vector x, then x transposed A x is greater than 0. And what we're going to do is we're going to actually phrase this as an optimization problem, where we start off with an initial guess at x, and then over subsequent iterations that converges to the value of x for which it's true that ax is equal to b. We're going to do it with something called conjugate gradients, which is an old approach but a good one, and is still used in machine learning approaches today. So for example, if we look at this paper, relatively recent paper on GPyTorch, so that's a PyTorch implementation of a Gaussian process. At the heart of it is a modified version of the conjugate gradients algorithm, so it's still very relevant to machine learning today. What we're going to do is show that solving this is equivalent to minimizing this function that's called the quadratic form. And we're going to write that as an f of x, which is equal to, so first of all, half x transposed ax minus beta transposed x plus some constant c. What we're going to do next is we're going to show that f of x has a single minima, and at that point is the value of x for which it's true that ax is equal to b. We're going to start off by calculating the derivative of f of x with respect to the vector x, which I'm going to write as an f dash x, and then just using standard vector calculus, this is equal to half a transposed plus a multiplied by the vector x minus b. And because a is symmetrical, that is equal to a x minus b. Okay, so if you set this gradient equal to 0, then what we're saying is that the point where the gradient with respect to x is equal to 0 is where ax is equal to b, i.e. it's the value of x where this holds. And now we're going to show that f of x just has a single minima as well. So we know that x is equal to a to the minus 1 b, although we're trying to solve for x without finding the inverse of a. What we're going to do is choose some point p that is not equal to x, and we're going to expand this term here. We're going to expand the f of x plus half p minus x transposed a p minus x. And essentially we're just going to expand this and see what happens. So first of all, we're going to expand the brackets. So we have f of x plus, and if you go through all the expansions, you end up with a half P transposed AP. Then have a minus P transposed AX. Then at the end, you're going to have a half X transposed AX. Okay, so again, that's equal to all of this stuff again. But what we're going to do is, here we note that by definition A times X is equal to B, because that's kind of the problem we're trying to solve. So here we get a minus P transposed B, and then this is still the same, half X transposed AX. Right, out here, so I'm going to try and perhaps speed this up a bit by copying all of this. Who knows if that's actually worked. We're now going to just expand this definition of f of x. So we've already seen this. So that's a half x transposed ax minus b transposed x plus c. And then adding all these other terms onto the end. And then finally, we're going to express this as, in terms of, rather, f of p. So if we take f, which we defined up here, and we write it in terms of p instead, we have a half p transposed a times p minus b transposed times p plus constant c. So if we have a look here, we've got a half p transpose p there, got a minus p transpose b there, we've got a plus c there, so that all gets kind of absorbed into this f of p. And what's left over is we have, well, let's have a look. These two things get added together, so we're going to have x transposed a times x. And then we've just got this thing left, which is a minus b transposed x. Okay, so things are getting a little bit simpler now. Remember that, so I'm going to write this somewhere else, from our definition of x is equal to the inverse of a times b. So that means that x transposed is equal to b transposed multiplied by the inverse of a, remembering that a is symmetric, so its inverse is symmetric as well. So we plug that in, it means that we've got f of p, and then this is going to go into here. It's going to have a b transposed a to the minus 1 multiplied by a multiplied by x minus b transposed x. Obviously, a to the minus 1 times a is the identity matrix, so you end up with f of p plus b transposed x minus b transposed x, which is going to be f of p, because these two things are going to be equal to 0. Okay, so quite a kind of long proof there, but what we're going to do is put it all together. So I'm going to take this thing, and what we've showed is that that is equal to f of p. Okay, so this means that f of p is equal to f of x plus this term here, where p is just some vector that is different from x. And remember that a is positive semi-definite, so that means that this thing has to be greater than 0. So from this, you can infer that, so we'll say this implies that f of p is greater than f of x. Okay, so the value x, which is defined as being equal to a to the minus 1b, we said is it lies at the minima of f of x, which means that as an optimization problem, it's actually relatively easy because f of x has just a single minima. So what we're going to do is start off with an initial guess at x, and we're going to essentially let it walk downhill in an effective way until we reach the bottom of f of x. And then by definition, once we get there, then we've found the x for which it's true that ax is equal to b. Okay, so we want to find the minima of f, the quadratic form. We're going to do that as an optimization problem, and one of the ways we can tackle that is with steepest descent. So what we're going to do is start off with an initial guess at x, let's say x1, and then we're going to try and walk downhill iteratively to create x2, x3, and so on until we get to the bottom of f, our quadratic form, at which point we know that we've reached a point where x is equal to a to the minus 1b. So as the name implies, we want to move in the steepest, towards the steepest downhill. So what we're going to do is we'll say that our approach involves setting our new estimate of x, so x at I plus 1 is equal to the current estimate, and then basically we're just going to move in a direction that corresponds to the steepest downhill. So it's the opposite direction to the gradient. So we have a minus, I'm going to introduce a constant here, which we'll come back to, so that's an alpha in this case, and f dash xi. So all we're going to do is take a step in the direction that's opposite to the gradient, i.e. the steepest descent. So that's the direction we're going to move in, and this is some constant which determines how far we're going to move in that direction. That's something we'll come back to shortly. So now it's a good idea to just to find some useful terms, which we'll come back to again and again actually. So I'm going to make a box here called useful stuff. So we've got some kind of important definitions. So first of all, I'm going to use x star to represent the point where f is minimized. So in other words, that is where a times x star is equal to b. So that's just so we can separate in our notation this optimal x from these x's that we're trying with our steepest descent algorithm. I'm also going to introduce the error. Okay, so that's simply the difference between our current guess at x and the optimal. So I'm just going to say that that's the, we're going to call that an e. The ith step of our algorithm is equal to x I minus x star. Okay, so they're vectors. So e is a vector, it's just the difference between our current guess at x and the optimal. And finally, I'm going to introduce something else called the residual. That's going to be an r. So the residual is, well, if we take our current best guess at x and we calculate a multiplied by xi in this case, then we're going to get something, unless we've arrived at the optimal solution, we're going to arrive at something that's different from b, so it's capturing that difference. So it's equal to b minus a times xi. Okay, and I'm going to put that in a box because we do end up coming back to that lots and lots of times, basically. Okay, so going back to our steepest descent algorithm, we've already calculated an expression for this gradient, or evaluated rather. So we know that the gradient of f at the point xi is equal to a times xi minus b. So that's right at the start of the video. And then if we look at our residual, the definition here, we can see that this is actually equal to the negative residual in the ith iteration. And so now our steepest descent algorithm looks like this. It looks like x at I plus 1 is equal to xi minus, or rather plus, because I have a minus times a minus here, plus a constant multiplied by the ith residual. So now all that's left to do is to determine what alpha should be. So we know which direction we're going to walk in, if you like. Starting from xi, we walk in a direction of the current residual. Now we just have to define or work out how far along that direction we should walk by defining alpha. So the best alpha will be the alpha that gets us to the minimum of f evaluated at xi plus 1. So what we're going to do to define the best alpha is we're going to say it's where the derivative of f at xi plus 1 with respect to alpha is equal to 0, because that's where we've, if we go beyond that, then we'll start walking uphill again, basically. So this term here are going to expand with essentially the chain rule, so I'll just write it down here. So what we've got is a delta f by delta xi plus 1 transposed multiplied by delta xi plus 1 by delta alpha I. So again, this is kind of vector calculus again. This thing, we've already used this a couple of times already. That gradient is going to be equal to the residual at iteration I plus 1 minus, in fact, so that's equal to minus residual at I plus 1 transposed. And this term, well, we can expand on this using our definition of I plus 1 up here from that is our steepest descent algorithm. So that term is equal to delta by delta alpha I multiplied by this stuff up here. So we have an xi plus alpha I residual. And then there's only a single alpha I in here, so that's equal to minus the residual at I plus 1 transpose multiplied by the residual at I. And we want all of that to equal to 0, okay, from up here. So the best alpha, so I'll write this down here. So the best alpha I, let's say, leads to Ri plus 1 transposed multiplied by Ri equal to 0. So in other words, it leads to these subsequent residuals being orthogonal. So now we're just going to expand residual I plus 1 transposed multiplied by residual I, write it in terms of alpha, set it equal to 0, and then we can find what the best alpha is. So the residual at I plus 1 transposed residual at I is equal to, so this is using our definition of the residual that was in the red box earlier. So the residual at I plus 1 is equal to b minus a times x at I plus 1, all transposed multiplied by Ri. I'm just going to expand that out, so that's going to be equal to B transposed Ri minus xi plus 1 transposed. A is symmetric, so A transposed is equal to A multiplied by Ri. And then again we're going to use our definition of xi plus 1 from our steepest descent algorithm. So that allows us to write that this is equal to B transposed Ri minus, so this is instead of xi plus 1, we're going to have xi transposed plus alpha I residual I transposed. Again, all multiplied by A times Ri. So it's by using this previous definition of xi plus 1 from our algorithm. That's how we can get alpha into here, basically. So now we set this whole thing equal to 0, and then we solve for alpha. So if we set it all equal to 0 and rearrange, what you end up with is that, let's say on the left-hand side, we have an alpha I, so it's these terms. So we've got an Ri transposed A times Ri, and that'll be equal to, what is the whatever's left here. So we've got a B transposed Ri minus xi transposed A Ri. Okay, so nearly there. There's an Ri common to both of these, so I'm just going to take that outside of these brackets. So we have a B transpose minus xi transpose A multiplied by Ri, and then this is actually our definition of the ith residual. So the whole thing comes out as being equal to residual, ith residual transposed multiplied by Ri. Okay, so it's now hopefully quite clear that you can solve for alpha, so you can find the best alpha, and what we do is we end up finding that the optimal alpha is this ith residual transposed and then multiplied by itself divided by this stuff. So that's an ith residual transposed A R I. Okay, so now we have our best alpha and our steepest descent algorithm is complete. So putting all this together, what we do is in the ith iteration is we start off by saying, well, what's the ith residual? So Ri is equal to B minus A times xi. We then calculate our best alpha, which we've already written, but I'll do it again just to be clear. We know that so we're going to move in this direction. The distance we're going to move is going to be given by Ri transposed Ri divided by Ri transposed ARI, so exactly as we've written here. And then we make the move. We say that xi plus 1 is equal to xi plus alpha I residual. Okay, and that is our steepest descent algorithm. So that's one way you could tackle this. You keep doing this and eventually your x will converge down to the optimal value for which it's true that ax is equal to b. And so that's one way how you can phrase this whole thing as an optimization problem and avoid trying to find the inverse of a. We can, however, do better than this. And in fact, if you think about different, so we're going to call them search directions. So in this case, our search directions are given by the residuals. That's the way when we're at xi plus 1, we're looking in this particular direction and then move by a distance alpha I. By changing those search directions, you can actually get some guarantees on convergence, and then that's from there we really go on to derive the conjugate gradients algorithm. So we'll start that in the next video with conjugate directions. But for now, we'll end on the steepest descent algorithm.